let's talk about the conservation of mass. If you have 1 kilogram of this blue liquid and 1 kilogram of this red liquid and combine it together, without even thinking too much, you know the total amount of liquid is 2 kilograms. If you had 4 kilograms of hydrogen and 10 kilograms of oxygen, then you end up with 14 kilograms of water. This is pretty much what the conservation of mass is. If you're doing math in the atomic levels, it's a bit different since mass and energy can be converted to each other, which is stated by this very famous equation. But for our purposes, which means general daily life and engineering applications, we can assume mass and energy to be conserved. In previous videos, we mostly talked about closed systems, so mass doesn't enter or leave the system. But now we're going to look at control volumes. What that means is that mass can cross the boundaries, but all we need to do is just keep track of it. Let's say you have a pipe like this and air is flowing through it. If we take a small area like this, how do we know how much air flows through it for a certain time period? For that, we study something called mass flow. In simple terms, we're looking at how much mass flows through this area for a certain time period. For example, 10 kilograms per second or 22 pounds per second. Mass flow is represented with the letter m and a dot on top, and it's called m dot. We can find it using this equation. Here, we're integrating over the entire cross-sectional area. This is density, and this is the normal velocity of the fluid. The problem is, integrating is tedious, so we need a general equation we can use quickly. For that, we have this. This is the density over the cross-section. This is the average velocity of the fluid, and this is the cross-sectional area. When we have a fluid flowing through a pipe, the velocity varies depending on where we're looking. So at the edges, it's pretty much zero, and velocity is the highest at the center. To find the average velocity, we can use this equation, but most of the time, this is going to be a value that's given. If we take a slice out of this pipe like this, notice how it's just a circle. So if you have a pipe or a circular opening, you can use the formula for the area of a circle to figure out the cross-sectional area. Next, we have volume flow. Instead of looking at mass that's flowing, we look at how much volume is flowing for a time period. For example, 20 cubic meters per second. Volume flow can be found using this equation. Just like with mass flow, we can use average velocity to find it without integrating. We can also relate mass flow and volume flow together using this equation, and that's also equal to volume flow divided by specific volume. You might notice that these are just the rate form versions of the normal mass and density equations. When we have a control volume, so an area where mass enters and leaves, then we can say the net change of mass is equal to the mass entering the area minus the mass leaving the area. We can express it like this. In rate form, we can write it like this. These equations are usually called mass balance equations. Imagine you have a box with an opening at the top and bottom. Right here is our control volume, with 10 kilograms of mass inside. From the top, we have mass entering at a rate of 3 kilograms per second. On the bottom, mass is exiting at a rate of 3 kilograms per second. The mass inside stays constant because the amount that enters is equal to the amount that's leaving. In a nutshell, that's a steady flow. In simple terms, in a steady flow system, the total amount of mass inside a control volume doesn't change with time. When it's one inlet and one outlet, it's called a single stream system. Some examples would be turbines, compressors, and pumps. In single stream systems, we can use this equation to find unknowns when it comes to steady flow systems. Usually, subscript 1 is used for inlet and 2 for outlet. We can further expand this equation like this to compare density, velocity, and area. If we have a substance that's incompressible, like most liquids, we can write our equation like this. Notice how we just cancelled out the density since it doesn't change, so we end up with volume flow. Keep in mind that volume may not always be conserved, so volume flow in and out can be different. This is especially true for things like air compressors. In the case of liquids, which tend to be incompressible, the volume flow is constant. Now let's go through some examples to see how we can apply the equations we talked about. In this question, we have a ventilating fan, and we're told to find the mass of air vented out in 1 day. Let's write down what we know. The volume flow rate is 30 liters per second, which is 0.03 cubic meters per second, and the density of the air is 1.2 kilograms per cubic meter. To find the mass, we will first figure out how much mass flows per second by using this equation. Let's plug in our values. So this tells us that 0.036 kilograms of air is flowing per each second. To figure out how much mass flows through for a whole day, we need to multiply it by 1 day, or 86,400 seconds. And that is our answer. In this question, we have a hot air balloon. We're told that air enters with a velocity of 3 meters per second, and we need to figure out how long it will take for the balloon to inflate to a diameter of 15 meters. Let's write down what we know. Initially, the balloon is filled with air that is at 120 kilopascals, with a temperature of 20 degrees Celsius. The initial diameter of the balloon is 5 meters. Now when the balloon is being filled, air enters at 120 kilopascals. The temperature is 20 degrees Celsius and it has a velocity of 3 meters per second. The diameter of the hole where the air enters is 1 meter. The final diameter of the balloon is 15 meters. We will also need the gas constant of air for this problem, so let's write that down too. That's the value right here. So here's how we're going to figure out how long it will take to inflate this balloon. First, we will find the initial and final mass of the air in the balloon. If we find the difference, we can figure out the amount of mass that entered the balloon. Then we need to find the mass flow rate, so how much mass enters per second. If we divide the difference by the rate at which mass enters the balloon, we can figure out how long it took to inflate. So first, the question is, how do we figure out the initial and final mass of the air inside the balloon? Let's focus on initial mass. Mass is volume divided by specific volume. How do we figure out the volume of a sphere? We can use this equation. Now we do have the diameter, but we don't have the specific volume, so let's figure that out. Air at the given parameters acts like an ideal gas, so we can use the ideal gas equation to figure out the specific volume. Let's isolate the equation. Now we can plug in our values. Remember, you need the temperature in Kelvin for this equation. Let's solve. Now that we have the specific volume, we can go back to our previous equation. Let's plug in our values. Remember, this is for initial mass, so we're using the initial diameter of the balloon. Okay, so this is our initial mass. We can use the same equation to find the final mass. Keep in mind that the specific volume will not change. So now we use the final diameter, which is 15 meters. Let's solve, and that's our final mass. Next, we need mass flow. In other words, how much mass is flowing into the balloon per second to inflate it. Let's write down our mass flow equation. We don't have the density, so we need to get rid of it. We can do it by remembering the basic equations relating mass, density, and volume. So first, mass is equal to density times volume. The second is that mass is equal to volume divided by specific volume. If we plug in one equation into the other, we can simplify it like this. So density is equal to 1 over specific volume. Now we can get rid of density by using this in our equation. It's hard to distinguish with the letters, but don't get specific volume and velocity confused. Also, we can replace cross-sectional area with the equation for the area of a circle, because remember, it's a circular opening that lets the air in. Let's plug in our values. Again, keep in mind, the diameter of the opening is 1 meter. Solving gives us the mass flow rate. This tells us how much air enters the balloon in kilograms per second to inflate it. Now that we have all the pieces, we will figure out how much mass entered the balloon. So this is the amount of mass that entered the balloon. If we can inflate the balloon at 3.36 kilograms per second, then all we need to do is divide the mass of air that entered by the rate of mass flow. We get about 723 seconds, or 12 minutes. In this problem, we have refrigerant 134A flowing through a pipe. We need to figure out a bunch of things, so let's start off by writing down what we know. The diameter of the pipe is 28 centimeters, or 0.28 meters. The refrigerant enters the pipe at 200 kilopascals with a temperature of 20 degrees Celsius, and the velocity is 5 meters per second. When it exits the pipe, the pressure is 180 kilopascals, and the temperature is 40 degrees Celsius. First, we need to figure out the volume flow rate at the inlet, so at the beginning of the pipe. Let's write the equation for volume flow. We can assume that the pipe is a perfect cylinder, which means the cross-sectional area is actually a perfect circle. That means we can replace the area with the area of a circle. Let's plug in our values. Solving gives us the volume flow rate at the inlet of the pipe. Next, we need to find the mass flow rate of the refrigerant. Let's write the equation for mass flow. So we have the same issue we had before, which is density. We don't have that, so let's get rid of it. Since we derived this in the previous question, I'm going to go straight into it. The problem is, we don't have specific volume. But we can find that from the table with our given values. Note that at the given initial and final conditions, the refrigerant is a superheated vapor. Our initial pressure is 200 kilopascals and the temperature is 20 degrees Celsius. So this is our initial specific volume. Next, we have a final pressure of 180 kilopascals with a temperature of 40 degrees Celsius. Now that we have the specific volumes, let's go back to our previous equation. The area can be found using this equation, so we can replace that as well. Now we can plug our values in. Solving gives us the mass flow. The last part wants us to figure out the velocity and volume flow rate at the exit of the pipe. Volume flow rate can be found using this equation. It's the same equation we keep using, which is mass is equal to volume divided by specific volume, but now it's in rate form. Let's isolate the equation. Keep in mind the mass flow rate is the same throughout the pipe, meaning it stays constant. Let's plug in our values. Don't forget to use the final specific volume we found earlier. Solving gives us our final volume flow rate. To find the velocity, we can use this equation. Let's isolate it. The area can be found using this equation. Let's plug in our values and solve. And that is our final velocity. That should cover the types of problems you will face when it comes to conservation of mass, mass flow, and volume flow. Thanks for watching and best of luck with your studies.